wants to read first? Jasmine, start us off. Again, the footnotes at the bottom we're not going to go through unless I ask you to, so you can ignore the footnotes, the little one at the bottom. You see a footnote?
Where do I start from the top?
From the beginning, yep. If you need help with a word, please ask. Some of the words are new.
Can we do popcorn reading?
Just start with differentiating right there.
Differentiation is the process by which when y is given us as a function of x, we can find dy dx. Like other mathematical operations, the process of differentiation may be reserved. Thus,
Reverse.
Thus, if differential y equals x to the fourth gives us dy dx equals 4x to the third, and then if one begins with dy dx equals 4x to the third, one would say that reversing the process would yield y equals x to the fourth. But here comes in a curious point. We should get dy dx equals yx to the third if we had just with any of the following: x to the fourth, or x to the fourth plus a, or x to the fourth plus b, or x to the fourth with any added constant. So it is clear that working backwards from dy dx to y, one must make provisions from the possibility of there being any added constant, the value of which would be undetermined until certain in some other way.
Okay, let's pause there. So, just to go through what we just said here, Christian, can you tell us what the key points are here?
They're saying that one, you can do the reverse of any mathematical operation.
Very good. So the first thing is, like, we know the inverse of multiplication is division. The opposite of addition is subtraction. So there are these inverse operations we're performing. So, go ahead. Give me an example. What's the key points from this, from what Jasmine read?
What we're saying is that if you take the derivative of y equals x to the fourth, and you get dy dx equals 4x to the third.
Okay.
That with that information, you're able to find what y is equal to.
So again, if we take the derivative, we go this way, right? And then we talked in class how if you want to do the reverse of that, instead of going down one power, you go up one power, right? And then we came up with the idea where there was this constant c that could be added on. So that's what is said here. So even if you had this, if you find the derivative of this, it's still 4x to the third, because a is just some constant, or c, or d, or k, whatever it may be.
Now, you see how like the function is just y, dy dx, that's the derivative?
Correct.
So is there like a notation for the antiderivative?
Correct, and that's the integral. That's that curly symbol we were talking about the other day. So if we start with this fact right here, we could say that the integral of this, integral, is this up here. So to go backwards from here to here, you take the integral of it. And this is where...
You have to add b and a thing.
You have to what?
When you take the integral.
You have a lower limit a and upper limit b, yes, and we'll talk more about that. Those lower limits, a and b, that we were talking about, that's how we can determine the value of the constant. Because you know how we said, well, if any of these could work, c plus a plus c, or just any other constant, what is that constant? That constant is determined from the upper and lower limits. That's where it comes from. Okay? Good. Now, the next part that we're about to take a look at here is this. If we remember the power rule, we say that, generally speaking, any power to the n, if you take the derivative of it, we bring down the n, we say n x to the n minus 1. Again, how does this work? If this was a 4, like we just had, the 4 comes down in front, this becomes a 3. Again, so think about it in your mind. We just did it a minute ago. Think about this. And it follows the rule perfectly. Whatever the power happened to be, we brought the power down in front, and we subtracted 1 from the power. That's right here. Are we clear? Again, you bring it down in front, and then subtract 1 from the power. So what you're really doing here is, you're multiplying by the old power, you're multiplying by 4, the old power, and you're reducing the power by 1. So if we're integrating, what's the opposite of multiplication? Division. So we're probably going to divide by something here. Okay? The new power, it turns out, and we'll explain how that comes about. Okay? And instead of decreasing the exponent, it's going to increase the exponent. So let's go ahead and take a look at an example of that.
It's really complicated when you have like.
Can you put that like x and
Guys, you can't both talk at the same time. You both just did that. You was talking first. Go ahead. You were talking first. I'm asking you to. Houston.
Can you put that in terms of x and n?
In terms of what?
X and n.
The integral? Yes, and that's what we're going to do now. That's exactly right.
was this before when we multiplied?
Yep, we brought up the dx, absolutely. I'm just trying to give you the formulas now, because we just did a bunch of examples that time, but now we're going to start getting to all the formulas we're going to need for integration. There's a lot, just like derivatives, it's the opposite of formulas. So if you want the integral, okay, if you want the integral of any function, let's say x to the n, and you always have a dx. Remember, does anybody remember where the dx came from?
That crazy wave.
Yeah, we did the dx. What did we do with it? We moved it up top, and we said that was dy. Okay? So if we wanted to do this, we'd say we take this, move it up over here and stuff. So right now, if we want the integral of anything powered, instead of dropping the power by 1, we're going to raise the power by 1. So the integral of this is going to be x to the n plus 1. Now, instead of multiplying by the original exponent, we're going to divide by the new exponent. And remember, at the end, there's some constant that appeared there. So this is going to be our formula here. This is the first formula you're going to use for integrals. Okay, and I'm going to do an example now so you can see exactly what I'm talking about. So if we have the integral of x to the second dx, what's x to the second if you raise it up 1 power? X to the third. And then what do I divide by? 3. Very good. And then add the c. Again, the rule simply says take the exponent, increase it by 1, and then divide by whatever that new exponent is. So this is the antiderivative, okay, the antiderivative. Are we good so far?
Yes.
Okay. Now, if we continue on the right side, let's start reading from so in the case. Can I get a reader from on the right side from so, Christian, from so in the case?
Oh, so in the case where dy dx is equal to x to the n, working backwards, we get y equals 1 over n plus 1 times x to the n plus 1 plus c. If differentiating the equation y equals ax to the n gives us dy dx equals an x to the n minus 1, it is a matter of common sense that beginning with dy dx equals an x to the n minus 1, and reversing the process will give us y equals ax to the n.
And let me prove that one now, because that one's a little bit confusing to read through. So here what you're saying is this. If you had some function and you were taking the integral of, we're calling it in this case a n to the x minus 1, if you were taking the integral of that, what is 1 more than n minus 1?
N minus 2.
1 more than. It's just n. Think about it this way. If you had 7 minus 1, what's 7 minus 1? But what's 1 more than 6? It's back to 7, right? So if you think about the number 7 here, 7 minus 1 would make this a 6, and when you integrate it, it would make it a 7. So when you integrate this, you're going to end up getting x to the n, okay, this an here is still here, but then you have to divide by n, don't you? Remember we said when you raise it a power, so if you're raising n minus 1, it goes up to n, but then you have to divide by the new exponent, and these cancel here, and that's all they're saying here. So you end up getting y equals a to x to the n. Oops. Okay, y equals ax to the n. So the idea is this. The derivative always lowers the power for power rule. The integral goes up a power. Now, with that said, what we really want to do today is take a look and say to ourselves, where else can we apply these rules? So can we apply these rules to cosines and sines? Can we apply them to the natural log rules? All that kind of stuff. And it's going to get a little bit messy here, because we're going to have to also use like a chain rule. Remember how we did the chain rule for derivatives? There's also going to be like a chain rule for integrals. And then later on, we're going to talk about something even more complex. Let's see, let's take a look at page 203, if you're looking on the top. Jump to page 203. The other stuff that's in here I'm covering, you're welcome to read a lot of it. We're not going to read every bit of this. Okay, jump to page 203. Now, this is one of the most important things we're going to have all year. If you take the integral of sums, it's the same as the derivative. You take the derivative separately. So if I asked you guys what the derivative of x to the third plus 2x to the fourth was, call that y, and I say find dy dx. What's dy dx of this? Good. You take the derivative of both, right? So the integral is no different. If you're taking the integral, you do the integral of one, you do the integral of the other. Now, if you do the integral, don't you get a constant? So you're going to get a constant from the first integral when you do it. You'll get a constant from the second. You can lump them together as one constant. Okay, and we'll talk about how that works. So if we take a look at from integration of the sums or the sum or difference of two functions. Can I get a reader from there, please? On the right side. Okay, thank you.
Let dy over dx equal x squared plus x cubed. Then dy equals x squared times dx plus x cubed dx. There is no reason why we should not integrate each term separately. For as many be seen in chapter 5, 6.
Doesn't matter, it's another chapter.
Yeah, we found that when we differentiated the sum of two separate functions, derivative was simply the sum of the two separate differentiations. So when we work backwards, integrating the integration will be simply the sum of the two separate integrations. Our instructions will then be, do I say integral of dy?
Yep, that's fine. And the integral of?
The integral of dy equals integral of parentheses x squared plus x cubed parentheses times dx, which then equals the integral of x squared dx plus the integral of x cubed dx, which then equals y equals 1/3 x cubed plus 1/4 x to the fourth plus c. If either of the terms have been a negative quantity, the corresponding term in the integral would have also been negative, so that differences are as readily dealt as sums.
Okay, so again there, notice, if you have an integral of two sums, you just break it up. Okay, you break it up just like it was differentiation. So when you're looking at x squared, it becomes x cubed over 3. When you're looking at x cubed, it becomes x to the fourth over 4. Okay, that's where the 1/4 and the 1/3 are coming from there. Okay, see the 1/3 and the 1/4? Those are coming from dividing by them, really. So the rule here you want to be thinking about is that the integral of x to the n plus x to the, let's say, m dx. Okay, that's what we're looking at. The integral of that is equal to the integral of x to the n dx plus the integral of x to the m dx. Okay? Again, you want to write down the fact that you can split them up. That's all you're going to be doing. Question?
So you're just distributing dx?
Exactly. You're distributing the dx to both terms, and you're really like you're distributing the sum or the integral sign, the sum sign to both terms. Okay? How do you get the 1/3? Well, if I raise this to the integral, it becomes x to the n plus 1 over n plus 1, right? So this is like the 1/3. Remember how we put it out in front instead? So if you're raising x to the third, see the integral in the example? X squared becomes x to the third divided by 3. Well, isn't dividing by 3 the same thing as multiplying by 1/3? Same thing with the next part. X to the third becomes x to the fourth over 4. But that's the same as multiplying by 1/4. So I can write this, and again, this is really plus c, when we would call this like really c1 here. And then next you'd have the x to the m plus 1 over m plus 1 plus c2. What we're showing here is that if we have two constants, they're just constants, right? So you can lump them together and write your final integral okay, as one constant at the end. Because a constant 1 and a constant 2, when you add two numbers, don't you get another number? And since we don't know the numbers, they're arbitrary. So if I said to you, Kenny, tell me, if I add 5 and 3, what's the answer? 8. If I add any two numbers, don't I get another number? So if I have C1 as some number, C2 is some number, it just sums together to some other number. So it doesn't, yeah?
Don't they mean something like when we start graphing them now? Like
sure.
Separately or no?
They do, but in the end, if you found them separately, if you actually found them separately and then you sum them together, you get the same answer anyway. So you might find this as 4 and this as 6, but if you did it together, you would find this to be 10. So we're doing like a shortcut on this, okay? This is widely used, by the way, sorry, widely used, lumping the constants together.
So is the x to the m plus 1, is that, are you basically saying same way you just put right there with the curves? versus x to the n dx plus x to the m dx?
Well, what I'm doing here, Houston, is I'm going back to my rule from the beginning.
No, not right here. Are you saying the same thing with those two different similar things?
So we're starting up here, then we split it up into two integrals. The integral of this is this, and then this reduces to this. These are all the same lines. So this is like step 1, then it reduces to step 2, which reduces to step 3, which the final answer is step 4. Now, clearly, once you get used to it enough, you can go from step 1 to step 4 instantly. Okay? Break it up in your mind, integrate them separately in your mind, and tack on a constant at the end of the whole thing.
How do we know if the original function is the result of a product?
Well, that's different. That's totally different, and we're not even there yet. If we have something where the original function, or the function we're looking at is a product, we have to then think about what to do with product rules. Totally different. Okay? So this is right now this is for x to some power. Okay? Just x to some power.
Wait, but when you say it's like, how do we know if it's the result of a product rule? Do we just look at it and see if the next derivative would be a product rule?
No. It's called substitution method, and we're gonna not spend, we at least need another week or two before we get to that.
Okay.
And that sounds crazy, but it's true. So for example, if you wanted the integral of something like x times, now this would be easy because you could just distribute the x, but if it was like x times x to the third plus ln of x, like that, and you want to find the integral of that, then we have to talk about what to do with that. And that's where you're going to have like a product rule, but it's a product rule for integrals, which is different than the product rule for derivative. Now, if you happen to have a derivative that resulted in two sums, it could have been the derivative of a product rule. It could have, but we don't know that necessarily. We're going to talk about one we will know in a little bit. For now, though, we're just going general rules.
Okay.
Let's see. Now, the next one I want to teach you guys about, we're going to start with the next part at the bottom. Can I get a new reader for the bottom from how to deal with constant terms? And how to deal with constant terms? Not all at once. Well, I can talk enough. I want you guys to talk a little more.
She's Friday, you still got to trying to see. How much do you
Jocelyn, thank you for volunteering.
Okay.
From suppose.
Suppose there's an expression to be integrated in constant terms such as this: dydx equals x to the n plus b. This is laughably easy. For you have only to remember that when you differentiated the expression y equals ax, the result was dydx equals a. Hence, when you work the other way and integrate the constant with here is multiplied by x, then you get dy equals x to the n dx plus b times dx. The integral of dy equals the integral of x to n dx plus the integral of b dx. Y equals 1 over n to the 1 times x to the n plus 1 plus bx plus b.
Okay, now, the key point here, we'll go through some of those examples, but the key point is that if you have a constant and you integrate it, you just tack on an x. And where does that come from, actually? So, if you remember, if we have y equals 5x, the derivative of this is just 5, right?
Yeah.
So if I have the derivative equals 5, to get the original, you just tack on the x. Now, obviously we put plus c here because it could be any constant. Where does this actually come from? If you have dy dx equals, I don't know, let's say 4, and you want to know what y is, well, we integrate this, we just said a minute ago, y will equal 4x plus some constant. What's really here next to the 4 then?
X to the 0.
X to the 0, which is 1. There's really, and I know you don't see it, but take a look. Anything, because you physically don't see it, it's not there. You don't see it here. There is physically nothing there. But any number to the 0 is actually 1. So if you do this now, raise this a power. What's 1 above 0? It's just 1. And then don't you divide by the new power, really? But do those really matter at all?
No.
They don't. So this is really a power rule. This is really x to the 0, which becomes x to the 1 divided by 1. But those don't matter. So that's why whenever you have a constant, its integral becomes just a linear function with a constant c. And take a look, isn't that a line? Ax plus b. Okay? And if you remember, Okay?
I'm sorry. But it will always have the C even if it's 0. There always has to be some
Sure,
constant.
sure, but C could turn out to be 0 and thus it would drop off.
Okay.
So remember graphically, people, if you had some sort of a, let's say, a line like that, its derivative is just the slope of that line. So let's say the slope of the line was 2, that means that the derivative is the line y equals 2. So now we're going from the line y equals 2 back to a diagonal line. That's here. If the derivative is some constant, y equals, in this case, 4, the integral of that would simply be 4x plus some little change in height. Okay, so this is the graphical representation where this would be the line y equals 4x plus c, and this is the line, in this case, y equals 4. Okay? Again, the integral of y equals 4 is y equals 4x plus c, which makes sense, because when we took the derivative of a line like this, it became a constant line. So the integral of a constant line is a rising line, or a falling line, some sort of diagonal line, a changing line.
So, when you write, you know, I'm gonna ask you just out wrong. But if you write the integral, like ever on a graph, we'll just write it as y equals, but we still use the integrals.
Well, here's what we're saying. The integral, we'll call this y1, okay? Call this y2. The integral of y1 is equal to this function. That's what we're saying here. The integral of this one right here is equal to this one. So you can write it several ways. Once we do enough, you'll see it doesn't matter. Okay. All right. Let's see. All right, if we look at 2 of 4, look at the examples there. The first one, the x to the 11, what would that become? X to the 12, right? But then what do you divide by 12?
2.
So 24 over 12 is what gives you the 2. Again, the answer is right there. Look at the answer. You got it though, you all got it. So again, raise 11, x to the 11 would become x to the 12, but then you would divide by 12. So you would end up with a 24 over 12, which reduces to 2. So you have 2x to the 12 plus the constant, okay? Looking at number 2 there, looking at number 2, you have quantity a plus b times quantity x plus 1 dx. Well, a plus b, okay, a plus b is just like a constant in the front. So I could just think of that. So again, a minute ago, we did the integral of 24 x to the 11, and we said, well, the integral of that is our dx. The integral of that turned out to be 24 x to the 12 all over 12, which is really 2 x to the 12 plus the constant. Now, that's a rule for numbers. If you want to write the general rule here, like they say in the next line, a plus b, or any constant in the front, times x2, in this case, what do they say, x plus 1? dx. Say again? Whoa! Would A and B are just some numbers, some constants.
No, I'm saying like the degree is a plus. Oh no, never mind.
Degree is like the exponent. So
What is this saying?
what this is saying is, what is the integral of some constant times some function of x? Well, this constant can just be moved out front. Okay, it can just be moved out front. Because if you think about it this way, when we took the derivative of a constant, the constant always gets carried down. So if you take the derivative, when we took, what is going on? Come on. When we took the derivative of, okay, we took the derivative of that, it just became what? Y prime equals 5 times 2x, really. Right? Because the derivative of x squared is 2x. So did the 5 really do anything? It just got carried down, right? So if you have some constant, and you're going to take the integral, it's just going to get carried down anyway. So you could think of this as, a plus b times the integral of x plus 1 dx. Okay? So again, what we're trying to say here, and what the book is trying to say, is that the rule is, if you have a constant in the front, whether it's a plus b, or, sorry, parentheses, or whether it's c plus d, or just some constant a, whenever you have an integral of something, and you have a constant, you can pull the constant out front. Okay, you can always pull the constant out front. Now, what would the integral of x become? What would the integral of x become?
Ooh.
X squared, because you raise it up over 2, or with a 1/2, good. Plus, what's the integral of x going to be? Sorry, the integral of 1 going to be? Sorry, I gave the answer, I know.
They're all plus C anyway. I'll see, you always have the
What about
concept.
the AB one?
No, I understand that.
You just drop off the DX?
What is the
Just get rid of it?
Guys, remember dx was the idea of a small distance x, and it comes about from dy dx, and you move the dx up? Okay? Dx is more like a, like imagine delta x getting smaller and smaller, that's what dx is. It's a distance, but it's getting smaller and smaller.
What is the x+1 in this case? Just a,
Some function.
okay, I just want to make sure it goes.
So all we're doing here is this, guys. We're trying to prove that, or show that, if you have a constant on the inside, you can always move it out front, then take the integral of what's left over. The integral of x is x squared over 2. The integral of 1 is just x to the 1 over 1. Okay, plus the constant. So this integral becomes that whole function there. And we still have a constant out front. And it treats it just the same way. So if a plus b, say a was 1 and b was 3, this would become 4. This is just the number 4. You would just distribute it back to every term. So again, whenever you have a constant, you move it out front. You could take the integral and then move it back out.
But that wasn't what you did right with dx. That's exactly what you said with dx. You distributed dx.
Not really though, Jasmine. That was for this one up here, where we had two functions we were adding together here. We did that a second ago, but I'm talking about now, what if there's a constant a in front of here? That's what I was saying. We're still having two parts, because we had x and we had a plus 1. And yes, we did integrate those and we distributed. But if you have a number out here, like a 5, you can bring the 5 out in front. Okay, so in this case, if you want to write a general rule for this, here's the general rule. If you have the integral of a x to the n dx, it's really a times the integral of x to the n dx. Okay, that's what the rule is really going to be here. It's the same rule as derivatives, the same rule as limits. Beginning of the year, we looked at our rules for limits. And we said if we have the limit of some function with a constant, we can move the constant out front and take the limit separately. Same thing here. If you want the integral of some constant times a function of x, you can move the constant out front and just take the integral of the constant of x, or the function of x. This obviously becomes what we said. This then becomes, you don't have to go further
Apply
about
to any rule?
anything. Whenever you have a constant out front, you can always just put the constant out front like this.
Okay.
Okay, Kenny?
Yeah, I was wondering because as you keep going into integrals, there are different rules which you apply for like products and
Yes,
yeah.
but always, whenever you have a constant, you can always come out front.
Okay.
First class, when I said, I'm gonna shoot.
Okay, so you can go to sleep in front. Oh.
He's going to sit in the front.
Maybe sleep for fun sounds the same as sit in front.
No,
It does.
listen to what you just
It
did.
does. Distorted.
Just
Just
listen.
Everything always sounds the same.
Distorted is speaking distorted.
All right, let's take a look at page 206 in the middle of the page. Page 206. So flip over, next page. On the left side, from another simple case. Another simple case. Can I get a reader? On page 206, we're on, guys? 206 from another simple case.
You don't got,
You don't have that on 206? Who wants to read? Aren't you guys all like AP literature or English?
I'm a regular English.
You don't read in regular English? You don't read in English?
No, we can call.
When nobody reads the
Silently?
book, yeah.
Make Carrie read. Just make Carrie read. Yeah.
It's your birthday?
Yeah, we're good.
Happy birthday!
Birthday.
If we finish this reading, maybe we can.
Hey, that means you're putting her birthday like.
Yes.
Sorry,
Sorry.
you don't get paid for my birthday.
That's
Come on.
Just make Carrie read.
Harry should read. Oh, you know what? I'll read and nobody wants
Did
to
you read yet?
Let
Do
her
you
read.
want to read?
No.
Just read.
Yes, he does.
Somebody.
Getting annoying.
Anybody.
Yeah, fine.
See, that's why I said we should do
He's
proper.
every fine.
Thank you, Carrie.
Find integral.
Thank you.
Which what?
Carrie's gonna do it. He's gonna do it.
Yeah.
Find integral of x plus 1 times x plus 2 dx. On looking at the function to be integrated, you remark that it is product of two different functions of x. You could think integrate x plus 1 dx by itself, or x plus 2 dx by itself. Of course you could, but what to do with the product? None of the differentiations you have learned have yield you to for the derivative of product like this. Failing such, the simplest thing is to multiply up the two functions and then integrate. This gives us the integral of x squared plus 3x plus 2 dx, and it's the same as x squared dx plus the integral of 3x dx plus the integral of 2 dx. And forming the integrations, we get 1/3 x cubed plus 3 over 2x squared plus 2x plus c.
Good.
Again, the idea here is this. We haven't learned or haven't talked about products. Even if you have a product, if you can ever multiply it out like that, do it. It makes it a lot easier on you. Just like, remember, with the quotient rule of derivatives, I always tell you guys, sometimes you don't have to take the quotient rule. So if you had like x to the 8th plus x to the 9th over x to the 3rd, you should separate it and divide it into both and then do a regular product rule, or power rule rather. Again, don't use a quotient rule for that derivative. For this derivative, write it as x to the 5th plus x to the 6th, and then take the derivative of that. So you would be dividing into each. Same thing goes here. If you ever have a multiplication where if you make the product or if you take the product of it, it makes it easier, please do it. Okay, it's a common mistake that people try to use the product rule, because later on we're going to learn how to multiply or integrate stuff like that, but there's no use to do it. Multiply it out, FOIL or box, whatever you call it, and then take the integral of both sides. Okay, or the integral of both parts. On the right side, all I want to do is go through some integrals that we're going to see here. The integral for this one, and the first one here, is the integral of x to the negative 1. But what is x to the negative 1 really written as, guys? 1 over x, isn't it? So this is really saying, what's the integral of 1 over x? But we saw when we took the derivative of something, we kept getting 1 over x. What was the thing we took the derivative of to get 1 over x? ln of x. So the integral of 1 over x is just ln of x plus the constant. Okay, that's our first rule, really. And you don't need the middle part there, okay? But whenever you have the integral of 1 over x, it's thinking of it as ln of x. Now, in your paper, what do they put? Absolute value of x, absolute value of x. There's a reason that's going to come into play. For now, you can leave this. If you'd like to put it there, that's fine. We'll talk about when that comes up. Let's see. The next one is not really that important because it's the same answer, but the ones that are really important that start to look at are going to be a little further down. So the second one is if we have the integral of x plus a to the negative 1. Now, here's the key I want you to notice. I want you to think in a second ago, when we took the derivative of something, we only used the chain rule if there was a number in front of the x, or if x was to some power. Because if we took the derivative, and I'll go up here to write this down, if we took the derivative of the natural log of x plus a, it's just going to be 1 over x plus a times the derivative of the inside. Well, what's the derivative of this inside? It's just 1. Again, the derivative of x plus a becomes 1 plus 0. So in this case, you don't actually have to use a chain rule because it just becomes a 1. So the same thing applies here. If we want to know what the integral of this is, we think of it as 1 over x plus a, which is what we have right here. Well, how did we get this? We got it from the natural log. Turn around. Let's go. We got it from the natural log here. So how do we get rid of this? We go back to here. So this turns out to be the natural log of x plus a plus c. Okay, again, when we took the derivative of the natural log of x plus a, it became 1 over that times the derivative of the inside. But the derivative of the inside is 1. So the same thing goes here. When you take the integral of this, it becomes the same thing, but the derivative of the inside, or the integral here, doesn't matter. Okay? So where does this come from? It comes from the derivative, as always. Every time you're looking at an integral, it's the antiderivative, or the opposite of the derivative. Remember the e function? When you take the derivative of e to the x, what was it? It was e to the x. So what do you think the integral is going to be? Same thing. That's the next one there. Okay, don't forget the constant at the end. Now, if you took the derivative of e to the negative x, what is the derivative? The derivative of e to the negative x going to become?
1 over e to the x.
Oh,
Why? Chain rule, very good. So this is really e to the negative x times the derivative of the exponent. What's the derivative of negative x?
-1.
Negative 1, right?
Yes.
So this is really times -1, which is really just negative e to the negative x. So in this case, if we look at the example next, if we take the integral of e to the negative x, the integral of e to the negative x, well, where could we have gotten the integral of this from? Well, if we look at this and say to ourselves, well, the integral of this is going to be a repeat again. But earlier, we multiplied by the derivative of the inside, or the derivative of the chain rule. Now we're going to divide by the derivative of the chain rule. Okay, we're going to divide by the derivative of the chain rule. So in our case, we end up getting this plus c, which is what you see on the 4th line there. Okay, you see that on the 4th line. I know it doesn't show it this way. Now on the 4th line, you're seeing this. Okay, which is the exact same thing. So remember, when we took the derivative, when you want to write down in words, if you want to write down your own steps, when we took the derivative of a chain rule, we multiplied by the derivative of the inside. When we take the integral of something where we'll have a chain rule, we're going to divide. We're going to divide by the derivative of the inside. Okay? So again, when you took the derivative, you multiply by the chain rule. When you take the integral, you're going to divide by the derivative of the chain rule.
You multiply by chain rule.
You multiply by the derivative of the inside from the chain rule.
You don't know about the first.
Yes. You would multiply by the derivative of the inside using the chain rule. On the integral, you're going to divide by the derivative of the inside using the chain rule.
You multiply by the integral using the chain.
That's what I need to write when I say it the first time. No, it says it right down. Thank you, Karen.
I just
Edgar. So we got to talk about something else in a while. It's not this. We're going to stop me this minute and we can talk about something else. Now, if we have the integral of e to the 2x, okay, e to the 2x. If I want to take the integral of this, it's a repeating function again, right? So what's the integral, or what's the repeat of this going to be? Good. And now I need to divide by the derivative of whatever the inside was. What was the inside of this considered to be? The 2x. So what do you divide by? You divide by 2. Again, remember for the chain rule for derivatives, we multiply by the derivative of the inside. Now for the chain rule of integrals, we're going to divide by the derivative of the inside. So if you had taken the derivative of this, it would have been e to the 2x times 2. Now it's e to the 2x divided by 2, because we're doing the integral. Again, remember, this is a side note if it helps you. The derivative of e to the 2x is equal to 2 times e to the 2x, because we repeat the function, and then we multiply by the derivative of the exponent. Well, for the integral, it's the inverse operation. So here, when we do this, we repeat the function, and we divide by the derivative of the original exponent. For chain rule, we're going to talk about, yeah. Eventually, we're going to start talking about something called substitution method, which incorporates chain rule also. Okay. The next two are the last two I want to get to for today, sine and cosine. And all I want you to think about is, when you did the derivative, what did you get? Okay? Remember, the derivative of cosine x was equal to negative sine x. Okay, the derivative of cosine was equal to negative sine. Everybody understand that? When we said when there's a c, it was the negative in the front. And if we remember also that the derivative of sine was equal to just cosine. Okay? The derivative of sine was equal to just cosine. So, if I ask you, what is the integral of cosine of x dx? And what is the integral of sine of x dx?
Actually, sine.
What's going to happen, guys? If we took the derivative of sine to get cosine, that means that if we integrate cosine, don't we get back to sine?
Yes, sir.
So this is just sine of x now, actually. And what is this going to become, though?
Negative cos.
Negative. Very good. Negative cos. So for integrals, what do you know about your negative stuff?
C is negative?
It's the reverse. Again, we took the derivative of c, we got negative x, right? Remember we took the derivative of anything like cotan or cosecant or cosine, it was always a negative? When you take the integral it becomes a negative when it's s. It's the backwards.
And also, if you had like a number multiplying, is that the a?
Yes. If you had like a number in front of here,
Yeah, it's the a, right?
yeah, and you would bring that out front. You don't need to worry about it.
Okay, then you multiply it back in.
Yes, at the end. Okay? So it's good to remember here that your derivatives and your integrals are inverse operations. That's why it's called the antiderivative. The antiderivative. Now, what I want you to do over the weekend, and again, I can check if you do this kind of stuff. The next part is a little reading, but it's on what we've done already. It's thinking about the integral as the area and looking at all the rectangle stuff. Okay? So you're going to see another 5 pages there, and you're going to see where the rectangles come about. I would like you to read through that. I'm not saying it's going to make perfect sense right away, but give it your best shot. When you get to page 215, page 215 is pretty much a giant footnote. So you don't need to read all that stuff. See that? See that footnote under 4 on page 215? Don't worry too much about reading all that stuff there. Okay, that's just a giant footnote there.
So,